Okay, so I'm just going to give you a quick introduction to TMS, and particularly the new setup that we've got at the CBU. So TMS is non-invasive, and it uses magnetics, unlike some other stimulation techniques, but it still induces an electric current within the brain. So we have electric current running through this cable and into this wire coil in this figure of 8 shape, which creates a magnetic field around this coil, and that induces an electric current underneath the center point of the coil within the cortex, and this has a spatial resolution around 2 centimeters, both across the cortex and deep into the cortex. And this field isn't static, it's dynamic, so it's turning off and on, giving a pulse of magnetic stimulation and a pulse of this electric current within the brain. And we can manipulate how you have those pulses, so the frequency and the number of those pulses, which gives us different TMS protocols that have potentially different effects. So you can imagine you could just have a single pulse of TMS, which wouldn't have a lasting effect, but you can do some kinds of studies using that, or you can create a lasting TMS effect by giving repetitive stimulation, so multiple pulses, and they can be in a pattern whereby you have, say, one every second, so just a standard repetitive pattern like these, or you can have bursts of high frequency stimulation with lower frequency. Those bursts happen at a lower frequency, so a pattern of stimulation like theta burst stimulation. And these different protocols can have different effects on the brain. Some are argued to be more inhibitory or more excitatory, and they take different amounts of time to complete. So this sort of around 10 minutes versus being quite quick. So what does TMS look like? Well, it doesn't actually look like this. And in fact, it no longer looks like this, because this was quite impractical to do tasks. So the modern TMS setup looks something like this. So we've got essentially just a generator producing this electrical current and putting it into this coil, and a computer interface for you to tell it what to do. You typically acquire a structural MRI scan before your participant comes to the TMS lab, so that using this camera and sensors on the pointer equipment and the coils, you can co-register the structural space to the participant's head and know where it is that you are stimulating at any moment. So why would you want to do TMS? Well, essentially because it allows us to make causal associations between a region of the brain and a task process. So unlike imaging, which is correlational and the activity may be epiphenomenal, we can talk about manipulating activity within a brain region and seeing the effect that that has on some process. And this is often done with 2 basic different approaches. So one of these is using this longer lasting repetitive TMS, patterned or not patterned, and then looking at the effect that this has on a task. And this is argued to simulate what might happen potentially if you don't have that brain region. So it's called a virtual lesion, because it's like you're simulating a lesion in a patient temporarily, but it allows you to compare within a participant having and not having that lesion. And that allows us to ask if a brain region is necessary for a task. So for instance, you can stimulate the anterior temporal lobe and see a reaction time slowing in a semantic task where it's thought to be involved, and not in a number task. A different approach to using TMS is to apply a single pulse whilst you're trying to do a trial of a task at different time points. So, for instance, here we have the trial onset, or 100, 250, 400, or 800 milliseconds later, and stimulating the same region. We can compare these times and see that there is an effect around 400 milliseconds on that semantic task, but not on that control task. So there's various factors you need to think about in designing a TMS study. So as well as the task and dependent variable that you think is important and the stimulation protocol, as we've mentioned, you want to think about the stimulation intensity, so how strong the TMS being applied is, and the general consensus is that the safest way to approach this is to consider the motor threshold of the participant. So that is, when you apply TMS to their motor cortex and get a twitch in their hand, how low can you turn the machine and still see that twitch, either visibly or based on the MEP amplitude if you record from surface EMG. Another critical question is how we locate the region that you want to stimulate. So you should have a general idea of what this region is from your hypothesis, but how do you get down to that precise region? The most common methods are to take an anatomical landmark, a group MNI coordinate, or an individual fMRI coordinate, so their peak when you run a task. That's of course more expensive, so probably the most common method is that group peak coordinate. And then a critical question is, what should you be using as your control condition? Let's first consider why that's important. So, I haven't mentioned so far, but the sensation of receiving TMS can be quite uncomfortable, and this isn't homogeneous across the brain. So this is worse in regions close to the face where stimulating incurs facial twitches. So you can see that in the frontal and anterior temporal lobes, you're much more likely to get those twitches and that discomfort. And this is important because it's correlated with the reaction time that you get on a task. It has a similar spatial layout as an effect of just changing the reaction time in an online task. Even in offline tasks, so where you have done that virtual lesion approach and you have the TMS before you do the task, you get non-specific TMS effects. So if you just look at the green lines here, this is a control task that's not thought to rely on any of the regions being stimulated, but you can see that there is a speeding up around 50 to 100 milliseconds in all those conditions. So we're getting non-specific TMS effects that may, in other cases, also relate to precisely where you have stimulated and how uncomfortable that is. So the kinds of controls that people use for this differ. Often people use a control site, which may be the vertex, or it may be the homologue of the region they're interested in, or it may be a completely different region. But it would be important in this case to make sure that that region is as uncomfortable as the area that you're interested in, and this is often not possible, for instance, if you're interested in those anterior temporal or frontal regions. Another option is a control task, but then you'd need to know that it has the same demands as the task that you're interested in, which may also be difficult. The ideal situation would be a sham, which you or your participant cannot tell is different and could get those same non-specific effects of TMS as your real TMS. But typically, sham coils simply simulate the sensation of having a coil on your head and the sound, but not that discomfort. However, there are new sham coils available that we think may be able to do this. They seem to be giving the same or similar discomfort levels even in these tricky regions, and that is the coil that we have available at the CBU now, which we think is potentially a opportunity for us to develop these methods and allow for appropriate controls. So there are a number of disadvantages of TMS, which I don't have time to go through all of them, but what I'd like to highlight is that many of these are simply the need for more methodological research. So the ability to have that appropriate control, the ability to know what the effect of different parameters are, and be able to interpret whether our null results are simply due to the choice of parameters or the fact that that region actually isn't involved, and whether the individual differences in responding are because there's no real effect and there's some noise in your data, or because those individual differences really reflect something important, like the thickness of someone's skull or the amount of GABA they have. So this is the setup we have here, and it's right for these kinds of methodological tests. Thanks.